Hello everyone. In this video we're going to learn about rational exponents, and we're also going to see how they tie in with the concept of radicals. So if we look at two expressions that we're familiar with, one being the square root of 25 and the other one being 25 to the power of 1/2. Now, on the left, we just have a radical, a square root, right? And on the right, we have a power. Now, what's different about that power is that the exponent is a fraction, which we may not have encountered before. However, we notice something interesting, that if we go ahead and square both of those, right? Notice that on the left side, the square root of 25 is just 5, and when we square it, we end up with 25, right? And on the right side, we notice that if we apply this rule, we usually use m inside and outside, so let's do the same. So in other words, the power rule for exponents, we get x to the mn, right? So here we're going to get 25 to the 1/2 times 2, which is 25 to the 1, which is again just 25. So it appears as though the square root of 25 and 25 to the 1/2 are the same thing, and in fact they happen to be the same thing. So if we generalize this notion, because it doesn't only work for square roots, for example, if you take the cube root of 8 and cube it, and then take 8 to the 1/3 and cube it, notice that on the left, the cube root of 8 is 2. When we cube it, we end up with 8, right? And on the right side, that we just get 8 to the 1/3 times 3, which is 8 to the 1, which is 8. So once again, it appears as though that the cube root of 8 is also the same as 8 to the 1/3. Now we generalize this notion by the statement that the x to the 1 over n is none other than the nth root of x. And of course, the nth root of x is the number you have to raise to the power of n to get x, right? So for example, what we mean by the square root of 16, when we see this, we ask ourselves a question, right? We say, what number raised to the power of this number in here? Well, you're going, there is no number. That's because there is an invisible 2. When the index of a radical is 2, we don't write it since it's such a common index. Is 4. So we're looking for the number that raised to this power gives us 16. So that would be 4. So when you do see this notation, remember that's called the index. The x inside, the number that's under the radical, is called the radicand. And the whole thing is called an nth root. So if you want to look at the whole expression and say it properly, you say the nth root of x, right? And basically it's the number that you have to raise to the power of n to get x, right? So for example, the cube root of 64, what would that be? Well, it would be the number that you would have to raise to the power of 3 to get 64. And if you remember from your table, that's 4, right? Or let's say you want to look at the fifth root of 625, right? Now, again, if you just basically break 625 down, find the prime factorization. We start with 5, we divide 625 by 5, we get 125. 5 again goes into that 25 times, 5 again, 5 times, and 5 again 1 time. So you can see the number you have to raise to the power of 4 to get 625 is indeed 5. Actually, in here, I miswrote that. I meant the fourth root of 625. So the fourth root of 625, that's what we want, not the fifth root. So the fourth root of 625 will be 5, you see, etc. So what is the fifth root of 32, right? Now let's look at 32. We notice that we have 2, 16, 2, 8, 2, 4, 2, 2, 2, 1. So on the left here, we have the prime factorization of 32. As you can see, the number, so in other words, 32 equals 2 to the 5. So when they ask you what number is it that raised to the power of 5 gives 32, your answer would be 2, etc. So, so we now discovered this interesting relationship between fractional exponents and radicals, right? So when you raise a number to the power of 1 over n, that's basically finding the nth root of the number that you started with. Okay, we should now be able to handle these very easily. So 25 to the 1/2, the first one, so remember, we can just write this as using this rule that x to the 1 over n equals the nth root of x, right? So that becomes the square root of 25. Remember, you can put the 2 in there or you can leave it out, right? When it's 2, it's optional. When you see a radical and you don't see any number in there, that means automatically it's a what? It's a 2. All right, so we get the square root of 25, which is 5, right? What number do you square to get 25? 5. So the tables that we looked at last time, if you recall, we made some tables for powers. They're useful here too, except you'll just look at them from right to left instead of left to right. So let's just do a quick table of cubes, for instance. Remember, we did 0, 1, 2, 3, 4, 5, right? So 0 cube is 0, 1 cube is 1, 2 cube is 8, 3 cube is 27, 4 cube is 64, and 5 cube is 125. So notice, if you look from left to right, you're cubing. If you look from right to left, you're taking the cube root, right? So for example, if I say to you, what's the cube root of 64? You can quickly look in this table and go this way, and you can see that it would be 4, right? So this is the cube of this number, and the number on the right is the number on the left is the cube root of the number on the right. So the number on the let's make sure we say that correctly again. The number on the right is the cube of the number on the left, and the number on the left is the cube root of the number on the right, right? So this table is useful in two different ways, right? So let's look at the second one. So this was number 1. Number 2, we're looking at 64 to the 1/3, right? So we know that that translates into the cube root of 64, and we just discussed that, right? That is 4. You can look at that table. What about number 3, which is negative 64, quantity negative 64 to the 1/3. In other words, we're going to look at the third root of, because the negative is inside the parentheses, it becomes part of the radicand. So we want to know what number is it that when we cube we get negative 64. Of course, that number would be negative 4, right? See, when you cube negative 4, what do you get? Negative 64. All right, so continuing with our problems, number 4, we have 16 to the power of 1/4, right? Notice that that's going to translate into the fourth root of 16. And of course, we know that the number we have to raise to the power of 4 to get 16 is 2 from our square table from the last video. Number 5, we have negative 16 to the 1/4. Now notice here, the negative is not being raised to the power of 1/4. Only the 16 is being raised to the power of 1/4. If we wanted to raise the negative to the power of 1/4 as well, we would have put it inside the parentheses like in the next example, okay? So in here, that negative is just going to carry. And the 16 to the 1/4 becomes the 4th root of 16. So we just end up with -2, right? Now for the next one, the -16 itself, all of it is being raised to the power of 1/4. So we're going to get the 4th root of -16. Now think about it. What real number do you know that if you raise to the power of 4, you get -16? If you think about it for a while, you'll realize that this is not a real number. And for the purposes of this class, we're only dealing with real roots. So that one, all we can say about it is that it's not a real number. Let's look at that in a little bit of more detail. All right, so when you say the 4th root of -16, some students incorrectly think, oh, that's -2, isn't it? Well, let's see. If you take -2 and raise it to the power of 4, remember, you're going to get 4 factors of -2, right? And you know that when you have an even number of negative factors, the outcome is actually going to be positive. So that's going to be +16 or just 16, right? So the 4th root of -16 is not -2. In fact, there is no real number, because if you take 2 and raise it to the power of 4, you get 16. You take -2 and raise it to the power of 4, like we showed here, you get 16. So there is no real number then you raise to the power of 4 to get -16, because any real number raised to an even power, or the even power of any real number, is going to be some, well, we should say non-negative out of respect for 0, right? Because it could be 0, so we shouldn't just say positive. So it's going to be some non-negative number, right? So therefore, there is no way you're going to have an even root of a negative number become a real number, right? So this, all we can say is that it's not a real number, okay? Notice we don't run into the same kind of issue with odd indices. So if you have the cube root, for example, of -8, no problem. What number is it that you can cube to get -8? That would be -2. Think about it. What is -2 cubed? That's -8. Because when you take a negative number and cube it, you get some negative result, right? Like so. Okay, so we don't have that issue with odd indices, right? We don't run into the not a real number situation with odd, but with evens we do, right? So if I say to you, what's the square root of -16? Same problem as with the 4th root. This one is not a real number, because there is no real number that you can square. Remember, that's the index when there's no number written. There is no real number that you can square to get -16. So therefore, all you can say is that it's not a real number. Okay, so we now know that if we have x to the power of 1 over n, that's the same as the nth root of x, right? So the question is, what if the rational exponent isn't just 1 over n? What if it's just some other number over n, such as, say, m over n, right? Well, notice that there are 2 ways you can look at that, right? One way is you can look at it as x to the 1 over n to the m, right? Or you can also look at it as, this is just playing with the laws of exponents a little bit, right? We can also look at it as x to the m to the 1 over n. Notice that if I multiply 1 over n by m, what do I get? I get m over n. So this is true. And if I take m and multiply it by 1 over n, I get m over n as well. So both of those expressions are equal to this x to the m over n, right? Notice that this one here, if I convert it to radical form, right, using this law right here, right, ends up being what? Ends up being the nth root of x to the power of m, right? This one, on the other hand, notice, remember, any number to the power of 1 over n, just think of x as any number, right? To the power of 1 over n becomes the nth root of that number, right? So it doesn't matter what that number is that you're raising to the power of 1 over n, it's going to become the nth root of x. For the purposes of our class, we'll deal with situations where the x or the base is greater than 0, so we don't run into any issues with not becoming a real number or having to need absolute values, etc. So in an algebra class, we'll go into more detail with that kind of thing, but for our purposes, we can deal with positive radicands and bases, right? So notice this is just going to become the nth root of, see, the expression here, instead of x, we have x to the m. So the x to the m is what's going to go inside the radical, right? Which is interesting because now we know that if we see x to the m over n, we can think of it as the nth root of x to the m, which is also the same as taking the nth root of x and raising it to the power of m. Now, this is actually a very useful conversion here, because this form in particular, the last one, is going to be very helpful to us, because instead of having to raise a number to the power of m to get a much larger number and then finding the nth root, what this is telling us is, hey, go ahead and take the nth root first and then raise it to the power of m. Let me show you an example. Let's say you want to deal with 64 to the power of 2/3, right? So I could use either one of those forms for my conversion to radicals for the purposes of evaluation, right? But if I use this one, notice I'm going to have to go with, notice that the denominator becomes the index and the numerator becomes the exponent here, right? So one way to remember that, notice the numerator is high and so is the exponent. So we say high goes high, right? So in other words, the higher position item here becomes the higher position item here. So the 3 is going to be the index, and then I'm going to have to square the 64 inside the radical if I'm going to use this form, right? So now I would have to sit there and figure out what 64 squared is and then find the cube root of that. But watch how much better it will be if I actually get clever and use this form, which means I can take the cube root of 64 first and then square it, right? Now you know that the cube root of 64 is 4. You square it, you get what? 16. Of course, this would have given us the same result, but notice how much more work we would have to do, right? We would have to do, the squaring of that, and then we get a much larger number, and then who knows what the cube root of that is. We would have to then do a prime factorization and all that. So this is the much more efficient approach. Take the radical first, then raise it to the outer power that you see here. So here we have 3 functions, exponential functions, and we want to do certain evaluations, right? So notice that for the first one, f of x is 64 to the x. So if you want f of 2/3, you're just going to replace x on the right side with 2/3, right? So we get 64 to the 2/3. Now this should look familiar to you, right? I just showed you how to do that. So that's going to become, remember, the index is going to be 3, the radicand is going to be 64, And we can either square inside, or better yet, we know that we can get the same result by squaring after taking the radical. So the cube root of 64 is 4, and that squared gives us 16, okay? Now, g of x is 3 times 16 to the x. So g of 3/4, we're just going to replace x on the right side of that definition of the g of x by 3/4. So now we're going to get 3 times. Now, notice that 16 to the power of 3/4, I'm going to take the 4th root of 16 and then what? Cube it. Now, remember, this 3 is just a factor. It's going to be multiplied by whatever this outcome is. So it doesn't play into the radical at all, okay? So we get 3 times. Now, we know what the 4th root of 16 is, right? It's 2. And we're going to cube that. So we get 3 times 8, which is 24. Again, we could have done this, right? We could have said that's 3 times the 4th root of 16, and we could have cubed that inside the radical, but you see, that would be a lot more unnecessary work, and then having to find the 4th root of a much larger number, which would be much less obvious than having to take the 4th root of 16, which is very easy. But it will work. You can try it on a calculator, for instance. We can get, let's see, so if we do the 4th root so here, let's see how this thing works. So we put that, and then there we're going to put the 4th root of 16 to the power of 3. Let's see, I want an exact answer, so I needed to hold shift, right? And notice we get 8. So 8 times 3, of course, is 24. So we could have gotten it that way, but since we need to show all the work that we do, we want to be efficient. Because remember, the purpose of the class isn't to learn how to just punch stuff into a calculator, but to develop our minds and learn how to do these things manually by hand, so that we develop some fundamental skills. So definitely take the more efficient route of taking the 4th root first and then cubing. So for the next function, h of x equals -5 times 9 to the x. We're going to evaluate h of -1/2, which means we're going to replace x with -1/2, like so, okay? So now we're going to get -5 times. Remember, before we evaluate 9 to the -1/2, we're going to want to make that a positive exponent. So what we will do is we'll bring that down, and it becomes 9 to the 1/2 according to this rule: x to the -n equals 1 over x to the n. So now we get -5 over, we're going to convert that to a radical. So the 9 to the 1/2, as we know, becomes the square root of 9. And we end up with -5 over 3, like so. All right? That's how we get these done. So just to quickly review the laws of exponents we've learned so far, remember the product rule for exponents. You multiply 2 powers with the same base, you keep the base, you add the exponents. To divide 2 powers with the same base, you keep the base, subtract the exponents, and it's always the top exponent minus the bottom exponent, right? And to raise a product to a power, we basically raise each of the factors in the product to that power. And to raise a quotient to a power, we raise both the numerator and denominator to that power. And a power of a power, you just keep the original base and you multiply the exponents. Let's go ahead and apply these a bit. All right, so notice here we're multiplying two powers. Here we go, lost the screen there for a second. So we're going to multiply two powers with the same base. So we know the rule x to the m times x to the n equals x to the m plus n, right? Keep the base and add the exponents. So we did that with whole numbers and integers already. Nothing changes when we get fractions. We do handle them exactly the same way. Notice that we need a common denominator, which is 6. So we're going to have to multiply 3 by 2, and that goes for 2 on the top as well. And this 2 we have to multiply by 3, and we have to make sure we do the same on the top, right? So we end up with base b, and then on the top, notice we now have 4 over 6 plus 3 over 6. So now those are like fractions. 4 plus 3 is 7, so we get 7 over 6, okay? So on this next one, we notice that we have a more complex situation. Now, we could take care of this first before we raise to the outer power, or we could just raise everything to the outer power and deal with that quotient rule later. That's probably the easier way to go. So 32 to the 2/5 times b. Remember, you're going to multiply these two exponents. 2 times 2/5 is, of course, 4/5. Down below, we have b to the 12 times 2/5, right? 12 times 2/5 is, of course, 24/5, right? So now we get 32 to the 2/5, and then b, we're going to go ahead and apply the quotient rule, which is going to be 4/5 minus 24/5, correct? So now I'm going to go ahead and take this and turn it into a radical using this rule, the fact that x to the m over n equals the nth root of x, the whole thing raised to the power of m, right? So we're going to get the 5th root of 32 and then square that, and then b. Now these two have the same denominator, this fraction, so we can just subtract the numerators and keep the denominator, the common denominator. 4 minus 24 is negative 20 over 5, right? So the 5th root of 32, as we know, is 2, right? What number do you raise to the power of 5 to get 32? We've done that before. It's 2. So we get 2 squared, right? And then b to the power of, that's negative 4, right? Negative 20 over 5 is negative 4. So notice that 4b to the negative 4. We're almost finished. Remember, we want our final answer to always have positive exponents. So we're just going to keep the 4 on the top, move the b to the 4 downstairs, and now we are finished. And we have no negative exponents in our final answer, like so. Okay, so make sure that as we do these, you try this on your own, even if you weren't able to pause because you recognize what needs to be done and then do the problem on your own and then watch the video later. Even if you had to sit there and watch it, okay, pause it now at least, after you watch it, and then go try to do it. Just write the problem down. You don't even have to do a completely different one. This will be just as adequate. Just write it down and try not to look at what was done at all, and see if you can get to the correct answer on your own. That's always extremely helpful to do that before you move on to the next problem. Otherwise, you're not really doing math. You're watching a movie, which is not very helpful, and it's not even a very entertaining movie, is it? As a movie, it's a failure. But if you're trying to learn, it can be quite effective. Okay, let's try another one. All right, here we have another one. And remember, we're going to do the standard approach that I've been suggesting. Just raise everything to the outer powers first before you do anything else. So notice that that's one thing that's better with actual whiteboards. They don't do this kind of a switch on you. All right, so, and they're not that touchy. Here we go. We're going to raise every factor to the outer power. So we get 81 to the power of 1/2 times b. We'll be doing some scratch work on the side. We're going to multiply 6 times 1/2, right? So 6 times 1/2, of course, is, notice, that's like 6 over 1. So 3 and 1. So it's just 3. Always cross cancel before you multiply fractions. And then c, we're going to multiply 20 by 1/2, right? So that's 20 over 1 times 1/2. Again, we cross cancel to get 10, right? Down below, we have 27 to the power of 2/3. Every factor gets raised to the power of 2/3, right? And then b, of course, remember, there's the invisible 1 here. We did multiply the exponent by that exponent, and 1 times 2/3 is just 2/3, right? Now we have b to the power of 12 times 2/3, so 12 times 2/3, right? So if we cross cancel now, 3 goes into itself once, into 12 4 times. 4 times 2 is 8. So we're going to need an 8 here. Let me go ahead and use blue. All right, and then c, remember the exponent now, we're going to have to multiply those two. We're applying the power rule, right? Over and over again. X to the m to the n equals x to the mn, right? So 9 times 2/3. 9 over 1 times 2/3. And notice 3 goes into 3 once, into 9 3 times, so we end up with 6. All right, so now we have done the first major operation we're going to do. So let's go ahead and separate the numbers and go ahead and turn them into radicals. So 81 to the 1/2, we know that's the square root of 81 over 27 to the 2/3. That's going to be the cube root of 27, and then the whole thing squared, right? So now we'll go ahead and apply the quotient rule to the b powers, and we end up with b to the 3 minus 8, right? It's always the top exponent minus the bottom exponent when you use the quotient rule. X to the m over x to the n equals x to the m minus n, right? And then c, 10 to the power of 10 minus 6, right? So the square root of 81 is, of course, 9, right? And the cube root of 27 is 3. And then when you square 3, you also get what? 9. And then b to the power of -5, c to the power of 4, right? Now these two are going to cancel out, so they're just going to leave us 1, right? And 1 times any expression is itself, so we're just going to get this, right? So all we're going to do now is get rid of that negative exponent by moving b to the -5 downstairs to make it b to the 5. And that is all we need to do there. And there's the simplified expression. Again, please make sure that you can get this done and handle it on your own before you proceed. This pretty much brings us to the end of this lesson. I just want to look at a couple of problems from homework. We've covered most types, but just a couple of notes and we'll be done. Okay, so this is not a problem that we haven't really handled in the lesson. I just want to show you what I expect to see as far as work is concerned on homework or on tests. For example, what I do not want is just this being punched into a calculator and then an answer provided. That's worth nothing, and as mentioned, obviously will constitute a cheating incident. To see with something like this is the conversion into radical form. So using this fact that if you have x to the m over n, that's the nth root of x, and then the whole thing raised to the power of m. So this is going to be the cube root of 27, and then you raise that to the power of 5, and that becomes 3 to the power of 5. Now, the 3 to the power of 5 portion, I have no problem if you type that into a calculator. That's okay. So at this point, you could just type it in. 3 to the power of 5, and you get the 243. So this part is no problem. But everything else that you see, I expect to see when you do a problem of this type. All right, so when you do a problem like this, be very careful. So the first thing that you need to understand is the fact that the negative is not being raised to the power of -1/2. So, but before we can do anything with the evaluation of this problem, we need to take that and turn it into a positive exponent. So we use this rule, right, to bring this 16 to the -1/2 down below and make it 16 to the 1/2. Now we go ahead and we keep carrying the negative, right? And we convert 16 to the 1/2 to the square root of 16. So we get -1/4. All right. Here's a problem which is not at all difficult. You just want to be really careful with situations where you have a negative exponent in the denominator, because we're just going to be applying the quotient rule, which says x to the m over x to the n equals x to the m minus n. And here the x is being played by 2, so the common base is 2. We write it and we subtract the exponent. So be careful not to write that, because that's not what we have here. It's always top exponent minus bottom exponent, which happens to be -5/3. So you're going to want to parenthesize that, and those two negatives are going to turn into a positive. So we're going to get 2 to the power of 6/3, right? Which is of course 2. And when it's something that obvious, go ahead and work it out, and you end up with 4. Okay? So that's that. All right, so on a problem like this, we're going to be using the distributive property. So we're going to distributive a to the power of 5 over 11 into the sum. So we have a to the 17 over 11 plus a to the 6 over 11. So just distribute as you would, with a times b plus c, right? What do you get? You get ab plus ac, the distributive property. That happens to be the left distributive property. So we go ahead and distribute, and we end up with a to the 5 over 11 times a to the 17 over 11 plus a to the 5 over 11 again times a to the 6 over 11. So we notice that this product, using the product rule for exponents, we keep the base, add the exponents, so that becomes 22 over 11 because the denominators are the same. So we keep the common denominator, combine the numerators because we're adding, remember? Let me just actually show an extra step. So here we get a to the 5 over 11 plus 17 over 11 plus a to the 5 over 11 plus 6 over 11. So now you can see that fractions which are alike because they have the same denominator are being combined. So we keep the common denominator, add the numerators, plus, and the same goes with the next expression. So we get a to the 5 plus 6, which is 11 over 11. Finally, we know that 22 over 11 is 2. and 11 over 11 of course is 1, and a to the 1 is of course just a, so that's why we just write a when we type in the answer. All right, so that should get you through this set. So make sure that you do all the assignment by hand. Do not want to use the calculator except in those, just basically figuring out a whole number power or something like that, as I mentioned in a previous problem. And that should do it. So I will see you in the next, and which is going to be our final video. So until then, stay safe.